Okay, John Woodward is next. One more talk before our last opportunity for Q&A. Awesome, thank you.
How are we doing?
Thanks, Ed.
Pension flagging, hanging in? I'll be fast.
Advance the slide and that's the list.
Okay, thank you. I'm John Woodward, Digitization Manager at the Museum of Comparative Zoology at Harvard. And I'm going to be talking about 3D reconstruction of embryos from histological serial section images. And I'm mostly talking about this cute little bat here. This is Special Collections number 1995 in our collection. So for those unfamiliar with the serial sectioning process, a specimen is embedded in paraffin or some other kind of matrix and then sliced into very thin sections with a microtome, sort of a glorified ham slicer. And then then the sections are laid out in sequence on the slides and stained with something that will add contrast to the anatomical features that you want to look at, and then covered with a cover slip. The reconstruction process that I'm going to be talking about is in some ways an incomplete reversal of sectioning. High resolution images are created and then aligned and stacked. The reconstruction process opens many avenues of analysis, including segmentation and measurements, creation of 3D models, all kinds of other stuff. I'm guessing that the machine learning folks are going to have lots of thoughts about what can be done to improve the process here, but also what can be done with the results. History of reconstruction, heavily abridged. On the left, you can see a model. This is a model created in physical space using a system of stacking wax plates. But it's basically the same process. The images of the sections were projected onto wax. The cutouts were made and then stacked cutouts. On the right, I've put a 3D surface model made from a micro CT scan. Micro CT reconstructions result in a stack of registered slices of density information. In some ways, this is a born digital version of the stack to plate process. So, recent research. Research scientists are still actively using and refining this technique to understand aspects of anatomy, evolutionary development, many other disciplines. I wanted to draw particular attention to a really fascinating paper by Benoit and Jasnowski, where they did drawings of the grinding face of a fossil and serially ground it, did a drawing at every stage of grinding. Realized partway through the grinding that it was a holotype of a new specimen that they were working on. So they continued with drawings, did very detailed images of the drawings, and then reconstructed both virtually and with a 3D printed model. So, value for natural history collections. 3D reconstruction represents a new way to make the specimen discoverable outside the collection. It can also yield information about the specimen itself. For example, the horizontal striations visible in this cross section here give us a clue about staining technique, which we hadn't noticed before. The number of horizontal bands corresponds to the number of slides in this series, and we think that the darker areas of those bands are indicative of more stain being applied to the first sections on the slide than the final sections. So you end up with this kind of like real striated appearance. My work has focused primarily on the Harvard Embryological Collection, also known as the Minot Collection, for its primary preparator, Charles S. Minot, and his students. It was created over several decades in the late 19th and early 20th centuries. The preparations are excellent, and the metadata is really complete, which turns out to be really important. And most of the series have a really nice, either a line drawing or a photograph, depending on the time when the preparation was done. And in either case, it's very important. having that photo documentation or that the prior knowledge basically of what the embryo looked like before it was sectioned up. So many collections hold serial sections preserved on slides, but not every collection has access to thousands of dollars worth of software and computing power. Therefore, I felt it was important to make this process work on my laptop using free software. So I used ImageJ and 3D Slicer as my primary software packages. Once acquired, the images must be, image acquisition, the first part of the process. Though the scans were done at very high resolution, this need not be part of the reconstruction process. The scan images were significantly downsampled, then individual slice images were segmented out manually. All credit goes to my colleague, Emily Blank, for this patient work. I think if going into the future, I would want to look into some machine learning alternatives for doing it, because it's very time consuming. Once acquired, the images must be registered. In most algorithms, this is done by matching pairs of images, beginning with a reference image and moving both directions through the stack as seen in the top diagram. So you choose a fixed reference image, then move the adjacent one to match it, and then proceed pairwise out from the middle. The graphic on the bottom progresses rapidly through a sequence of sections from the bat embryo. You can clearly see the difference from before and after. Image registration is done by applying one or more transforms to the moving image in every pair to make it match the fixed image. The most common types of transforms are shown in the table here. I'm mainly going to be talking about the rigid, which is translating in XY space and also rotating, and the elastic, the last one listed here, where there's sort of mesh deformation that you can apply to make the pairs match. When reconstructing specimens with any amount of curve to them, the original shape is unattainable without prior knowledge of the specimen. This is referred to in Mendelein et al. As, quote, the banana problem. As shown in their diagram, when the banana is sectioned, if the section images are unaffixed to a reference point, the pairwise matching of the faces will result in a cylinder. And on the gray banana there, the spectral remnant on the right is the banana reconstruction that could have been if only we had prior knowledge to compare the section images to. But there are further inherent difficulties. The process of cutting and preserving sections results in warping, tearing, inconsistent staining, changes over time, and other, quote, artifacts which alter unpredictably the topology and extension of anatomical structures. Because of these deformations, it's unlikely that any given section can serve as a reliable reference for the registration of the others, and it's impossible to know anyway, absent prior knowledge. In other words, registration of serial section images is inherently difficult. Elastic registration is likely to compound the lossiness of the sectioning process, and perfect registration may be impossible. All that said, many smart people have worked the problem from different angles and have written software based on resulting algorithms. I recommend the linear stack alignment with SIFT as one plugin that's easy to use, gives good results, and works quickly. It's limited to linear transformations only. It doesn't do elastic. Second, TrackEM2 has a baffling array of menus and options, but it's worth it. It can register with linear and elastic transforms as separate steps. So you can do one linear to sort of line things up, and then a separate elastic transform to like fine tune your results. It has no RAM restrictions, so it's very good for limited computing power, and it doesn't alter the original data. I prepared a sort of stepwise click here, click there kind of protocol for using TrackEM2, and that link at the bottom will take you to that. So what can go right? Or can you start the movie up there? Yeah, thank you. So this is the results of rigid registration of 732 bat embryo slice images. The original line drawings and the slide label metadata, the original line drawings, these guys on the right, And especially the slide label metadata provided a helpful reference for the slice interval. That is how far apart the slice images should be placed. And thus how pudgy or stretched out the bat embryo should be. And then from here, the stack can be cross-sectioned in any arbitrary plane. It can be measured internally and externally, cleaned up and smoothed for 3D printing, all of that stuff. So in natural history collections, we use the language of science, but fundamentally we're in the memory business. And I'm thinking about specifically Dave's question or this sort of formulation from before, like who is it for? I think that it would not have been possible for the folks who prepared these slices to know that, and especially who made very detailed drawings to know that these would be important for reconstructing in a sort of virtual space. But we can't know what our work is ultimately for. It's tempting to think of this kind of thing as like a techno apotheosis of the specimen, but I see it more as like a bridge between islands of memory to connect both from the sections to between the sections and the line drawings, but also to unknown uses at some unknown point in the future. And that's it. And I'd like to thank those folks who helped with various aspects of this project. That's it. Thanks.